Good evening, colleagues. We are Team Indecisive. I'm Jerry.
Kaylee.
Coulter.
Emily.
Tonight we are presenting to you the best option for a replacement filtration design. It's for the water treatment plant in Japan that was destroyed by the recent magnitude 9 earthquake and resulting tsunami. 400,000 people were left without water treatment. Not only is there now seawater in the drinking water source, but there's also large amounts of debris along with radioactive elements. However, our project does not deal with radioactive treatment. Our design must work towards the goal of clean, safe drinking water. Here's a diagram of a typical water treatment plant. Surface or groundwater enters the water treatment facility and gets coagulated. It moves on to the clarifier or settling tank and then enters the filter. This is the unit operation we chose. After the filter, it gets disinfected and then moved to a reservoir for distribution. The main goal is that the water treatment effluent is safe, healthy drinking water.
When looking for drinking standards for Japan, we looked to their version of the EPA, which is the Ministry of Health. Here we found that Japan's standards are based on standards recommended by the World Health Organization. For healthy drinking water, total dissolved solids must be less than 600 milligrams per liter.
For our filter design, we are assuming the large debris and other particles were removed in the first steps of the treatment plant to 1,200 milligrams per liter of dissolved or small solids left. The filter we chose to model is a rapid monomedia sand filter. This is the best way to get the most water treated, the quickest and cheapest way. It also takes up less space than a slow sand filter, and space is an issue in Japan. The filter effluent will be up to standards, which is less than 600 milligrams per liter.
We decided to focus on filtration because this is a vital step in water treatment. This is the removal of particles too small to see, such as negatively charged colloids and pathogens. Safe drinking water is essential to life, and we want to work with something that can have a direct effect to help the people of Japan.
This is the typical cross-section view of a sand filter bed. To solve this problem, we had to make a few assumptions based on similar filters already in existence. The rate at which we need to treat the water is 6,233.3 meters cubed per hour. This is the flow rate into the treatment plant. The values we had to calculate were Reynolds number, coefficient of drag, porosity, expanded porosity, and head loss. We found these with general equations learned in class. This is a schematic of how the bed expands due to backwashing. We also calculated the removal efficiency of the filter, which is based on critical velocity and average velocity. The removal efficiency of our filter is 99.9884%, meaning that almost all of the solids left in the water are removed, and it meets safe drinking water regulations.
We found the total surface area of the filter beds to be 519.44 square meters. Our average filtration rate is 0.2 meters per minute. The maximum filtration rate is 0.24 meters per minute, which occurs when one bed is removed for backwashing. The number of filter beds we need is 6. This means the cross-sectional surface area per filter bed is 86.57 square meters. Based on these calculations, our filter dimensions are 10 meters by 8.66 meters, with a height of 3 meters. Here's our complete unit operation schematic viewed from above. The water flows in and disperses evenly between the beds. It flows into the sand bed, passes through the filter, and is collected in an outflow trough to move on to the next treatment process. Here's a vertical cross-section of the filter. The filter bed depth is 1.2 meters of sand. The 3-meter height allows for bed expansion. Under the filter bed is a gravel support on top of a perforated metal plate for support. The effluent is collected below this. We hope you liked our design so we can help the citizens of Japan as quickly and safely as possible.